Probably 2 parts is better for the audience also. Especially given in this case, because the 2 parts are going to be somewhat unrelated in a sense. So, okay. So we are back to tight cuts, but now we will talk about the tight cut decomposition procedure. Okay. So what is this procedure? If you have any tight cut in a non-trivial tight cut in a matching code graph, what you can do is you can consider the 2 contractions. Because it is a non-trivial cut, the 2 contractions will be smaller graphs, and because it is tight, they will be matching covered. Yeah? So you'll get 2 smaller matching covered graphs. Now if any of these has a non-trivial tight cut, you can repeat this. For example, in this graph, is this a tight cut? Not easy to check if you check all perfect matchings. But is it a barrier cut or a 2 separation cut? If the answer to any of those is yes, then it is a tight cut. Yeah? Is it? Yeah? 2 separation cut, everybody agrees? This is a 2 separation cut, therefore it is a tight cut. And now I'll get 2 smaller graphs. One graph, this will become a single vertex, and the other graph, this whole part will become a single vertex. Yeah? Let's draw one of them. Which one do I want to draw? Let's see. I'll draw this side. Okay. So I have these vertices, I have this vertex, I have this vertex, I have this fellow here, and I have this fellow here. Is it okay? This left side? Yeah, I have drawn the entire graph induced by these vertices. Now I need to draw the last vertex. Maybe I will color it. And where does it go? It goes here. It goes, this one is fine. It goes here. Okay, these 2 are taken care of. And now these 3 edges, all 3 go to this vertex. Is that correct? That is one tight cut contraction with respect to this tight cut. Yeah? Of course, there is another one. I'm not drawing that for now. Let me just look at this. This again has non-trivial tight cuts. If it does, then I can again get 2 smaller graphs. Well, I think I see a non-trivial tight cut. This will give us K4 and one more graph. Yeah, so we'll get K4. Let's just quickly draw K4 here. That's okay. And now let's draw the other graph. So what is the other graph? This is all okay, and then this becomes a single vertex. Yeah. So we got from this original graph G, we got a G1 which I have not drawn, and we got a G2, and from G2 we got a G21 and a G22. And again there is a non-trivial tight cut. Yeah. So I get 2 more graphs. This becomes a single vertex. So this is my G221, why not? And now this whole thing becomes a single vertex. G222. Yeah. But of course I have not done the whole tight cut decomposition. I have just completed this branch. I have not even drawn this graph, and then I have to complete that branch also. Yeah. Okay. Turns out this is actually going to stop right away. This one will stop right away because I will immediately get, maybe I'll just draw this, why not do it? Okay, so what do I have? I have something like a 6 cycle. I have this vertex in the middle that goes here, here, and here, and then everything. I have. No, I'll get more stuff. Yeah, I'll get a vertex. Oh, I see. Okay, this is more interesting than I wanted it to be. Okay, fine. So I have one more vertex here. Okay, and then I have this vertex as well. This is going from here. This. Is that okay? And I have a contraction vertex which goes to this fellow. It goes to this fellow, the next one. No, it goes here. 1 and 2 edges. And then I have 2 edges going to this last vertex. If I'm not mistaken, this is the correct drawing. And the shrunken vertex is which one? I messed up everything. This is a shrunken vertex. Is it correct? Yeah? Yeah, this is our graph G1. Yeah? Does it also have tight cuts? It does, right? Okay, where is the tight cut? Or maybe I missed some edges, did I? Is this a degree 2 vertex? That seems strange. Why is there a degree 2 vertex? I think I messed up this drawing. There are 2 degree 2 vertices, right?
And if there is 4 vertices, that is because of that.
There is a degree 4 vertex there.
Okay. Which one? This one?
In the new one.
In this graph?
Yeah.
There's a degree 4 vertex, this one.
No. Like below the degree 2 vertex.
Below the degree 2 vertex, this one.
Yeah, so that edge should be up the.
This edge should go here?
Yeah.
Like this? No, it's correct. But there's again a degree 2 vertex.
That is also the same thing, like you have to connect the degree 2 vertex with the.
I see. I should have not drawn this edge.
Yes.
I should have drawn this edge. Now it's okay? Yeah? And now does it have tight cuts?
Outermost face is a triangle.
Outermost face is a triangle. 1, 2, 3. And that is a shore of a tight cut. One way to see it is to color the vertices here. So let's see. You are saying that the outermost shore is a triangle. Outermost face is a tight cut shore. So you mean that this is a tight cut. Yeah? And this will give us again 2 contractions. One will be the cube graph and one will be K4 up to multiple edges. Yeah? I'll just, in the interest of not making a mess further, I'll get a cube graph G11, maybe there are multiple edges, I'm not sure, and I'll get K4 up to multiple edges, that is my G12. Yeah? Okay, so what we did is we started with a matching word graph. We took one non-trivial tight cut, we got 2 smaller matching word graphs, we kept doing this. You can think of this as a binary tree, which basically stops when you get matching code graphs that do not have any non-trivial tight cuts, also known as bricks and braces, right? So every matching code graph, you can decompose it into bricks and braces using this procedure. That's clear? Of course, what is not clear, and it was actually not clear to people for years apparently, was whether this is unique or not. And Lovász basically proved that in a certain sense it is unique. Let me just tell you what that sense is. So of course the cuts you choose, that need not be unique, right? I could choose one cut and you may choose another cut. There is no reason for the cuts we choose to be unique, to be the same. But the result you get at the end, will that be unique? That's the question. Right? So here is an example where you will not get the same graphs. Here is a small example. Manoj may choose this cut. Anjali may choose this cut. And after this, you won't get any more. You will actually get K4 in both cases, right? Up to multiple edges. And can you all draw the graphs and check that they are not isomorphic? For the yellow cut, draw the two graphs. And for the pink cut, draw the two graphs. And check that the two graphs you get for the yellow cut, they are not the same as the two graphs you get for the pink cut. Keep the multiple edges. Yeah? Not the same? Not the same? Not the same? Okay. In one case, you get an edge with multiplicity 3. You get a pair of vertices u comma v such that there are 3 edges joining them. And in the other case, you get no such graph. Is that correct? The underlying graphs are of course the same. In both cases, you just get K4s, 2 copies of K4 up to multiple edges. Yeah? Turns out, you will always get the same list of graphs if you consider the underlying simple graphs. So this is Lovász's theorem. That is the next main goal for this course. Lovász in 1987 we'll call this the unique tight cut decomposition theorem, although it should technically be called uniqueness of the tight cut decomposition theorem, but that's too long. Any two applications of the tight cut decomposition procedure to a matching covered graph G yield, or if you like, produce the same list of bricks and braces up to multiplicities of edges so if I get 2 copies of K4, 3 copies of the Peterson graph, and 1 copy of K33, then Srijit will also get 2 copies of K4, 3 of the Peterson graph, 1 of K33. The only difference is our multiple edges may be different. Yeah, but if you take the underlying simple graphs, it will be the exact same list. Yeah. And this basically tells you that there is something very, very fundamental about the tight cut decomposition procedure. Right? This kind of uniqueness result, it sort of reminds you of the prime factorization uniqueness. Why not? Right? That's a fundamental result. Okay, so this is what we will prove next. What's the big problem with proving such a statement? There is some inherent problem with the statement itself. I'll tell you what the inherent problem is. The inherent problem is there's a procedure, also known as algorithm. That's the problem with this statement. So how do you prove this kind of statement? It would be nice if you can throw out the procedure from the window. Right? If you can throw out the procedure from the window and replace it with something more abstract, that may actually help us. Right? Because the procedure, I mean, you took one cut, I took another cut, this person took another cut. How do I compare all these procedures with each other? Right? It would be really nice if we can get rid of the procedure somehow and think of it in a much more abstract way. Right? Because in a procedure there's also sequence. Which tight cut will you choose first? Will you choose this one? So what are the cuts I used here? Let's do one thing. All the cuts we took, let's map them back to the original graph. Observe that, in fact this is the point I want to make here. Observe that every cut in any of these smaller graphs corresponds to a cut in the original graph. Let's do it. So this cut that I took here, it corresponds to this fellow. This cut that I took here, it corresponds to this fellow here, which then corresponds to this fellow here. I'm going upwards in my tree, right? So I got this, and I got this. Okay, I got these, good. And now let's look at this mess that I created here. This cut here, it is corresponding to what? 1, 2, 3. It corresponds to this. Is that correct? Yeah. So what we have done is we have taken all the cuts, we have lifted them to the original graph. And now what we have is a family of non-trivial tight cuts in the original graph. Yeah? This is a family of non-trivial tight cuts. Let's see how many we have. We have C, we have, I don't know, C1, C2 and C3. Observe that C, C1, C2, C3 is a family of non-trivial tight cuts in the original graph. When you have two cuts, you can talk about whether they are laminar or crossing. Right? We talked about this in the earlier lectures. Are these laminar or crossing? Any two in this family. Any two in this family, they are, right? Yeah, they are laminar. So this is a family of, I'll call it a laminar family. By laminar family, I mean any two in the family are laminar, pairwise laminar. This is a laminar family of non-trivial tight cuts. You all agree? We have a laminar family of non-trivial tight cuts in the original graph. Yeah? Okay, and now let me ask you, of course in this family, if I just give you the family, not a sequence, if I just give you the family, then does it define things uniquely? Can I choose any cut from here? And can I choose them in any order? Or does the order matter? See if you can figure out. Does the order in which you choose the cuts, if I give you a laminar family of non-trivial tight cuts, and I tell you, hey, these are your non-trivial tight cuts, apply them and get the tight cut decomposition. Then my question is, does the order matter? Or does it not matter? To think about this, it may help some level of abstraction. Maybe this is too concrete. So think about it this way. I give you two laminar cuts. Now I don't even need tight and all that. This is one cut and this is another cut. They are laminar, which is why I have drawn them like this. Right? Otherwise I would draw like this. Now if I take the C contractions, in one of the contractions, this will still be a cut. Then I take the D contractions in that graph. Or if I reverse the order, if I first take the D contractions, then in the other graph, I'll get a C cut. Then I take the C contraction. Does it really matter? Does it matter whether I choose C first or whether I choose D first? Alright? Yeah, you all agree? The order doesn't matter. So that is why family is okay. I don't need a sequence. I can just take a family. Yeah? So we are slowly getting rid of the procedure. Just take a laminar family of non-trivial tight cuts. There's one more small point. We took the entire tight cut decomposition until we got to the bricks and braces. What does that tell you about the family? Maximal. That means the family should be maximal. If I can add any more cut to this family, then I would have added that, no? Yeah? Right? So, not only is it a laminar family because I took the entire tight cut decomposition procedure, this is also a maximal such family. So what is the summary? The summary is that every application of the tight cut decomposition procedure basically corresponds to a maximal laminar family of non-trivial tight cuts and vice versa. There is a bijection. The advantage here is that there is no procedure. It's just a family of tight cuts. The order in which you choose them, it doesn't matter, as you have already convinced yourself. Yeah? So, given any two maximal families of laminar non-trivial tight cuts, we want to prove that they are in some sense equivalent. They will give us the same list of bricks and braces. Yeah. So this is what we are trying to prove. We are trying to prove that any two such families are equivalent. Yeah. So let's say G is a matching covered graph. Let's say script C and script D are maximal families. Maybe I should put laminar later. Maximal families of laminar non-trivial tight cuts. We will say that they are equivalent if they produce the same list of bricks and braces up to multiple measures. Lovász proved that any two are equivalent. They are both maximal families of laminar non-trivial tight cuts. Yeah. And I'm going to prove that they are equivalent. Any two such families are equivalent. Okay, so the good news is we don't have to think about procedure and all that, sequence and all those things, right? But we still have to prove things, right? There's still work to be done. We're not done. We're far from being done. Okay. Let's try to finish some cases, then we'll continue on Wednesday. On Wednesday, we'll finish the proof. Right? Are there any questions, concerns regarding the statement itself? Or this another way of looking at it? Yeah? Okay? Alright. So, we will prove by induction on the order of the graph. If I get a smaller graph, I'll just conclude it is true. Yeah? By induction on order. Right? So the statement we are proving is, in any matching curved graph, if I give you any two such families, they are maximal families of laminar non-trivial tight cuts, then the statement says that they are equivalent. Right? Of course, if the graph is a brick or a brace, then we are done, right? If the graph is a brick or a brace, then the families are empty, there's nothing to be done, so this is fine. So the interesting case is when the graph is neither a brick nor a brace. There are tight cuts, therefore a maximal family will have at least one cut. Right? At a priori, we don't even know that maximal families should have equal cardinality. Even that statement we don't know right now. That is a consequence of this statement. If we prove this theorem, then it implies that a maximal family, its cardinality is an invariant of the graph. Right? It's basically number of bricks and braces plus 1. Is that correct? Minus 1 plus 1. If I get 2, then it is minus 1. Yes, minus 1. Yeah. Right? So we don't even know right now that the cardinalities are equal, but that will be a consequence of the deeper result we will prove, or the stronger statement will prove. Right? So, if G is a brick or a brace, done. Otherwise, assume that they are not. It's not a brick or a brace. We have script C and script D, and each of them is non-empty. Each of them will have at least one cut because the graph is not a brick or a brace. Yeah. Okay. All right. So now let's try to think about some good cases. So both C and D are families, maximal families of pairwise laminar non-trivial tight cuts in a matching curved graph. We know that the order doesn't matter. We know that the order in which we choose cuts, that doesn't matter. So what would be nice? If I give you some condition on C and D, then can we just finish the proof by induction? One common cut. If there is a common cut in C and D, then Manoj is saying that we should be able to finish the proof. Think about it. Is that true? Is that false? Supposing they have a common cut. Okay? So, case 1. I can never write this properly. Their intersection is not empty. So they have some common cut. Then can we finish the proof easily? Yeah, everybody sees that? Right? You have to think about how to get your smaller graphs G1 and G2, and you have to define families for G1 and G2. You have to get it. You have to get a maximal laminar family for G1. You have to get a maximal laminar family, 2 of them, 2 for G1, 2 for G2, and then because they are smaller graphs, right? So there is work to be done. I will let you think about it. So it turns out that is actually true. So consider a common element I don't know, let me call it capital F, and try to finish the proof. We'll complete it next time, but in the meantime you can actually think about it yourself rather than me filling up the details. Right? So see if you can write down the details and check that everything is okay. Right? Okay, so if they have a common cut, then we will be done. That's the statement. Okay, good. Supposing they have no common cuts, right? There's no common cut between these two families, then intersection is empty. Then we still need to work. Case 2 is not case 1. Yeah? So we still need to work with this case. So now can we somehow find another nice condition? So common cut was a good condition. Common cut, you finish the proof. But maybe there is no common cut. Then can we still come up with some condition, a nice condition, that would still help us finish the proof? Right? So yeah, just raise your hands if you have any ideas. So see if you can think about some nice condition that would still allow you to finish the proof in some sense by resorting to case 1. And if you have an idea, raise your hand, I'll come and talk to you. Right? So see if you can come up with some nice condition on C and D, and using that condition, so it is an assumption. If that assumption holds, then you are able to again finish the proof using case 1, right? And then case 3 will be that condition also doesn't hold. It's neither case 1 nor case 2. Okay. But yeah, if there are any ideas, I can come and chat with those of you who have anything to say. Otherwise, we'll conclude soon. Anyone else? Anyone else? We've seen it a couple of times. Okay, you can think more about it, but yeah. Anybody else? Okay, so most of you are thinking about things like laminar and crossing. So that is a good idea. Think about laminar and crossing. Let's just see what we can figure out. Both of these are maximal families of pairwise laminar non-trivial tight cuts. So if I take one cut from C and one cut from D, does that imply that they are laminar? No, that's not true. They may be laminar or crossing. If I choose one cut from here and one from here, there is no reason for them to be laminar or crossing, because this condition of being laminar is for the families. You can't say anything about two elements, one from here and one from there, right? So yeah. But what is true, one of the things that Manoj pointed out, if you take some cut from C, it can't be laminar with everybody in D. That is true. It will have to definitely cross with somebody in D. Yeah, I don't know how to use that fact, but that is true, right? But at the same time, two arbitrary cuts from C and D may be laminar or crossing, and that's the direction you want to think in. All right. So you can think about it, and we will continue this proof on Wednesday. And my hope is to finish it on Wednesday, but we'll probably use the whole 2 hours. Yeah. Okay. Any other questions or concerns before we wrap up? All okay? Okay. Thank you.